original address into internal buffer. As the second step, after saving the byte and the address, the debugger replaces the original byte, the first one byte, the starting byte, not inside the instruction. The starting byte of the instruction is overwritten with this one byte, CC. As a third step, the debugger, at this second point, as the second step is finished, the software breakpoint is completed, is set into program, and debugger just needs to wait until this breakpoint triggers. So this is the first step. Debugger waits. Wait for debug event under Windows, or ptrace, or sys wait for under Linux. The third step. The fourth step, the interrupt-free handler is triggered, and this interrupt-free handler gets the address, not this address, but one byte after this address, because the interrupt-free is the trap type of exception. So it is triggered after this instruction is executed. So the interrupt-free handler gets address one byte after the starting address of instruction. So the debugger subtracts 1 from this address, and it gets address X. This address X is the starting address of the instruction CC. The instruction is reported after debugger subtract 1 and get the start address of this instruction. Okay? And then, as the sixth step, debugger checks its internal buffer whether this address X is stored and matches. If no such address found, so it is not breakpoint put into program by debugger. It is breakpoint incompiled in the program. It is this second choice. If such address in internal buffers are found, it means that it was software breakpoint put into program by debugger, by these two steps. And in this case, it's 8. If such address found, it was our breakpoint putting into program by debugger. In this case, the debugger must restore the original byte which is saved at the address X. It replaces the original byte back. This one disappears and is overwritten with original. Okay? It restores the original byte at address X, and then it decreases the instruction pointer in the program, because after triggering interrupt 3, the instruction pointer is increased, is 1 byte after this, and after subtracting 1, the instruction pointer is pointed at the start address of the instruction. And this is everything what debugger has to do when it needs to handling software breakpoint. At this point, everything is restored. There are other features in debugging which are not very much known. Much people knows about them, and this is that we can watch addresses causing control transfers. Everybody knows that that is very difficult to trace back the error. Yeah? Tracing forward is extremely easy, stepping and so on. But what happens before the exception? How to know the addresses before? We could jump in here from this, from several points. Yeah? And this feature helps to record the last branches, changing of instruction pointer. Yeah, there are traces back what happened before the exception. And the CPU records this instruction: jumps, calls, returns, conditional jumps, jump if CX is 0, loops, far jumps, far calls, return for fars, interrupts, exceptions, returns from interrupts, system calls, system returns, non-maskable interrupts, system management interrupts, resuming from system management. We just need to enable one bit in one register. But I suppose that nor Windows nor Linux has this one bit
You can do it if you do your driver work, and it can be very, very useful if you're dealing with unpacking programs, for instance.
So the name of this register is debug control MSR, and the value is the same in Intel and in AMD. They made perhaps an agreement not to make references. So this is the sample how to read, how to set this one bit in this control register. We put this value into ACX, we execute it, read machine status register, we turn on bit 0, and we write it into this control register back. This sample enables this bit 0. We can enable bit 1, and it is the complication of simple stepping which I told you about. That single stepping can be much more difficult, not exactly only single steps. So we have 2 bits to set to make life complicated. Setting this bit 0 orders the processor to start to record the addresses of branches, jumps, returns, calls, and so on, taken before the debug exception occurs. So recording traces back what happens before exception. The processor automatically disables. This is the same like when I told you about single steppings of disabling the track flag bit. The processor disables the control transfer recording when interrupt 1 occurs, and it prevents the instruction inside interrupt 1 handler to override these records in these machine status registers. And before exciting the debug exception handler, software can set this bit to 1 to re-enable the recording mechanism. So after enabling this bit 0 of this control register, the source and destination addresses of control transfer events before the control is given to interrupt 1 are saved by the processor. Branches, interrupts, exceptions. And we have 4 registers, 4 records, what happened before the interrupt 1. These are 64 bits read-only registers. And here we are then, these 4. Here, please, everything is. This is the sample how to read the last branch from IP register. This one. We load ACX with this value, and then we execute read machine status register. And then we can say ADX is the high double word, and EAX is the low double word. Because the address is 46 bits, and the higher half is recorded in EDX, and the low double word is in EAX. And put together, the address is 46 bits. bit 1, this one, when we enable it, then we change the behavior of single stepping. Normal behavior is that single steps occurs on every instruction. But when we set this bit, then single stepping changes. It doesn't occur on every instruction, but only on branches. So we can make bigger single steps, not small, or bigger, only to branches. I didn't saw this in any debugger. It requires in kernel mode to enable this one bit. I didn't see it in any debugger, nor in Windows, nor neither in Linux. But it is possible to do it. Perhaps we can make our own kernel.
I've seen it on Windows, but it requires a driver board.
Oh.
It was used for some automatic unpacking.
Oh. We can write drivers in. So this is, and now we are finishing theoretical. We don't have 46-bit machine to show you my debugger in the work, but the debuggers, my debugger supports symbols. What does it mean, symbol? If we load executable into debugger, we see a lot of hexadecimal numbers, addresses, and so on and so on. And the symbols are helpers to translate the hexadecimal address into label. This address is in memory when the program executes, and this label, this is some text in your source of program. This type of symbols are supported in my debugger. Under Linux, it is the debug with arbitrary record format, which is supported. And under Windows, there are two ways how to obtain symbols. One is thanks to this DLL, but this is not very suitable for us as flat assembly programmers. It is suitable for programmers in C. And I discovered that we can easily make labels under Windows by making exports in executable. It is the same way as DLLs. And after this, we can make symbols very easily under FDBJ. Summarization about breakpoints. Breakpoint must lie on the starting of the instruction. Breakpoint mustn't lie inside the instruction. We have two types of breakpoints. Software breakpoints by overwriting one byte in memory with this byte. It has the disadvantage that it modifies memory's program. Program as an executable could easily detect this breakpoint by simple calculating self CRC, and if some byte is overwritten with this one, the CRC is incorrect. In this case, we can use hardware breakpoints because hardware breakpoints doesn't modify memory. And if we use hardware breakpoints, we can get correct CRC of the program because no one byte of memory is modified. But the disadvantage is that we have only 4 hardware breakpoints, only 4. And these software breakpoints, they are limited only with size of memory. We can increase buffers and to have software breakpoints several millions. And the advantage of hardware breakpoints is that we can watch reading or writing into memory or in kernel into ports, as I showed you. It is not possible by software breakpoints. They triggers only on instruction execution. Hardware breakpoints may be triggered by accessing memory or ports. I have some samples included in my debugger, where you can use hardware breakpoint to watching the first word of kernel free to DLL, because viruses likes to access this start of kernel 32, this signature MZ, and after accessing this start, the viruses can look for making imports from kernel DLL. Yeah. And viruses often accesses this beginning of this DLL. So we just prepare hardware breakpoint watching this signature MZ, and after program accessing it, it is almost some virus trying to do ugly jobs without imports, without manual.
And a normal system RAM does never access that address? Only viruses access that address?
Almost viruses. I prepared some sample there. It is not virus, it is only a concept how to viruses.
Some compressors and software protection will do as well, but it's a pretty dirty technique.
Yes, a normal system RAM doesn't access that.
I haven't seen anything normal do it, but some compressors.
If some of your programs accesses the signature word MZ at the beginning of kernel DLL, you have to vary whether it is not virus. Yes. But the sample included in the debugger isn't virus, it is only a sample of how viruses behave without imports. Summarization about steppings. We have two possibilities how to do steps. The smallest one is traced into. It is by setting the trap flag bit of flag registers. It is the smallest possible step. The smallest. And then we can make bigger steps with the name steps over. It is in my debugger by pressing F7, and this is by pressing F8, just like in old turbo debugger. This step over behaves as this smallest step, but in these three cases, it behaves in an other way. When you execute step over on these instructions, then step over puts software breakpoint after and allows the whole cycle to complete. The repeating string operation, the calls or the loops. And when you execute trace into at these instructions, you will have to do trace into several times until the whole repeating string operation or the procedure of the loop completes. You have some samples included in debugger when you can watch differences between these two steps. And there is the third step, but this is not used in my debugger by setting this one within one control register. This is not used in my debugger. But
that's a question. Loco is asking, how can you detect if your processor supports the only break on branches feature? I think it was introduced in early machines, but is there a way to detect the presence of it? Or?
Yeah, I am not sure now, but I suppose that CPU could be used to obtain this information. But I am not sure really. But this feature is included several years into manuals. This is not news, it is an old information, but this type isn't very much used and is perhaps forgotten. We will finish. There are two groups of assembly programmers who really need debugging. The first are programmers doing big, boring, exhaustive job, and this is the reason of doing a lot of mistakes. The second type of programmers who really need a lot of debugging, these are programmers doing a lot of mistakes because they just started to learn assembly. I tried to do debugger as easy as possible to help beginners. But the impairment of beginners is rapidly increasing thanks to debugging. This is the specimen sample of the first type of programmers. He's doing very big project and he's boring. He does a lot of mistakes because he is exhausted. This is he. And this is the second type of programmers. The beginner just started to learn assembly. Thanks to your attention.
Thank you.